Okay, yesterday we learned the first test for infinite series, convergence, divergence. What was it? Geometric series, yeah. So if you spot an infinite series with the sigma and the infinity at the top, and it looks exponential, okay, which is geometric, if your base, which we call the ratio, has a magnitude of 1 or larger, the series diverges to either infinity or negative infinity. And if the magnitude of the base, which we call the ratio, is less than 1, then it's like an exponential decay. Then the series converges, and it converges to the first term over 1 minus r. And r can be negative. So if r is negative, then the denominator turns into 1 plus r when you plug it in. Okay? So we did that on example C. All right. So here is now the next one, and this is actually going to be the first test that you always do. There really isn't a flow chart necessarily, but if there were, this would be at the top of the list. Okay, this is the first thing you consider because it's a time saver. Now, unlike the geometric series, which was a two-way test, meaning you could definitively determine if the series converged or diverged, the next test, called the nth term test for divergence, is only a test for divergence, which means it's a one-way test. So if the test doesn't apply, then you can't make the other claim. You have to use a different test. So because this is only a test for divergence, it doesn't help you determine if something converges. So here's what it says. If the limit as n goes to infinity of your rule of sequence, that is the terms, if your terms don't go to 0 eventually as n goes to infinity, then the series, the sum of those terms, diverges. End of story. And it does make perfect sense when you think about it, because we mentioned it yesterday. In order to have a shot for the sum to converge to a finite number, you have to get to a point somewhere down in the sum where you're adding nothing, right? Plus 0, plus 0, plus 0. So those terms have to approach 0. If the terms don't approach 0, then you're getting to a point where you're adding 1 or 2 or 3 every time, and that's just going to make it really big. But it is a one-way test because it is a necessary but not a sufficient condition. Just because the terms go to 0 doesn't mean the sum converges. We saw that up here on example, which was example 5 yesterday. We looked at 1 over n and 1 over n squared. Both of these rule of sequences go to 0, don't they? But we learned that the sum of 1 over n diverged. It did go to 0, it just didn't go to 0 fast enough. Whereas 1 over n squared did go to 0, bless you, fast enough that the sum converged. So you got to be careful. If the terms go to 0, now it's time to roll up your sleeves and try a different test and see if the series converges. But if the terms don't go to 0, game over. All right? It's a one-way test. So example 9, determine whether the following series converge or diverge. Well, let's come up here and do example B first. 8B. Some of these series are going to fall under multiple tests. If you look at 3 halves to the n, what would be the limit as n goes to infinity of 3 halves to the n? It goes to infinity, right? And infinity is not 0, so the series diverges. And this time we could say by the nth term test. Is that the same result we got yesterday with the GST? Yeah. So if it falls under more than one umbrella or more than one test, you should get the same result for each test. That's how math works. All right? So you could have actually, if this were a problem that you kind of just came up upon in the future, if you didn't recognize it as a GST, you could have done the nth term test and gotten the same answer. All right, so now example 9a. We got the infinite series, the limit as n goes from 1 to infinity, of 2n plus 3 over 3n minus 5. A lot of these show up as multiple choice questions, so your intuition or your lack of formal notation can take you far. What is the limit as n goes to infinity of this rule of sequence? 2/3. Does 2/3 equal 0? No. So you're going to get to a point in this series where you're going to be going plus 2/3, plus 2/3, plus 2/3, which is going to make it grow infinitely large. So if this were a multiple choice test, you know that this one would diverge, okay? And it actually diverges to infinity. If you had to justify it, here's what you would say. You would say the limit as n goes to infinity of 2n plus 3 over 3n minus 5 equals 2/3, which does not equal 0. So the series diverges And then you would say by the nth term test. If these things show up on a free response, it's going to be like one part of a free response question, like part B or part C. And you will have to go ahead and give the evidence and name the test. Okay, but the nth term test typically is not one of them. There are some tests that show up more frequently than others on the free response. So we'll practice the notation, the argument, but sometimes just looking at it and saying the series diverges is good enough. Because if it's a multiple choice question, you have like Roman numeral 1, Roman numeral 2, and Roman numeral 3, and they'll give you like 3 series, and the question will say which of the following series converge. And then, of course, your answer choices are combinations of 1, 2, and 3. So you could tell very quickly. All right, let's look at letter B. Infinite series, and we've got n factorial over 2n factorial plus 1. Does this series converge or diverge? It diverges, right. Now, we didn't do this one a couple days ago. We have the same factorial, n factorial over n factorial. So much like n cubed over n cubed, or n to the fourth over n to the fourth, when they're growing at the same rate, it's going to be leading coefficient over leading coefficient. So what do you think the limit of the rule of sequence is? As n goes to infinity? It's 1/2. Yeah, it's 1/2. And, of course, 1/2 is not 0, so this series diverges. I'm not going to go ahead and write it all out anymore. The series diverges. Or how about this? We'll just write diverges. Or hey, how about this? We'll just put D for diverges. That work? C for converge, D for diverge. We know the reason. We would have to write the limit and then say that 1/2 is not 1. All right, letter C. 3 to the n minus 2 over 3 to the n. Diverges. It's in this section, so it maybe is going to diverge, but let's see why. Maybe it's not as intuitive, or maybe it is. You have 3 to the n minus 2 all over 3 to the n. You could split it up and do it that way, but again, notice you have 3 to the n and 3 to the n. Those are both exponentials, and not only are they both exponentials, they're the exact same base. So this would be another case where it's leading coefficient over leading coefficient, which is 1 over 1, which is 1. So does 1 equal 0? No. So this series is going to diverge. And again, it's important to make the difference, to note the difference between the terms and the series. The sequence converges to 1. But because the sequence or the terms converge to 1, the series, the sum, diverges. All right? So if you didn't recognize it as leading coefficient over leading coefficient, this is another one where you could split it up. 3 over n over 3 to the n minus 2 over 3 to the n. This becomes 1, and what happens to this as n goes to infinity? It goes to 0. So either way, you end up with the sequence converging to 1, so the series diverging. All right, how about this dude? Converges. Why? By the nth term test? What is the limit as n goes to infinity of 1 over 1 plus 1 to the nth power? 0, okay? So now do we say then the series converges by the nth term test? No. If you ever hear someone say something converges by the nth term test, they're either trying to be funny to make a joke and you laugh, ha, good one, or they have no idea what they're saying, okay? Because the nth term test is not a test for convergence, okay? So we'd have to find another way. Now, because the terms go to 0, this thing now has a shot at converging. And it actually still does converge. Why? How do we know that? If we rewrite that as 1 over 1.1 to the nth power, this now is a what type of function? It's geometric, right? It's a geometric function. You can write it as an exponential function, essentially. And 1 over 1.1 is equal to r, which is what compared to 1? Is it less than 1 or greater than 1? It's less than 1, okay? So we know that the series actually converges. Hey, not only do we know it converges, we know it converges to what? We can actually find the sum. For a geometric series, we can actually find the sum. So remember, it's going to be the first term. The first term you always get by plugging in the starting value of n, which in this case is 2. So that's the numerator. It's 1 over 1 plus 1 squared, all over 1 minus, what is the ratio? What is r? Is the ratio 1.1? No. That's why it's important to write it in this form. R to the n. So the ratio itself is 1 over 1.1. So 1 over 1.1. And that's the exact answer. Okay? If you had a calculator, you could type it in, or maybe even just call 1 and 1/10. Call it, what, 11/10? And then you can maybe get the answer a little bit more quickly. All right, so there you go. If something converges, it's not by the nth term test. If it's a geometric series, not only if it converges can we say it converges definitively, we can find the sum. All right, so good so far. Any questions on anything, 1 through 9, or about burritos? Did anyone look at the Chipotle website to see if they are having any kind of burrito day specials? No? Okay. The series such as this. Okay, so here's kind of a bonus little series. I kind of like it. This is not on the BC test, but it's a pretty cool series. 1 minus a half, plus a half minus a third, plus a third minus a fourth. We call this a telescoping series. Okay? Anyone ever seen a telescope? Yeah. Nowadays they're fixed. Okay? But back in the day, maybe they weren't maybe we called them spyglasses. I don't know. Now, spyglasses aren't the ones you kind of get in the catalog that allow you to see around corners. A spyglass is a telescopic glass that folds up, and whenever you want to use it, you pull it out. Kind of like a retractable, telescoping antenna. Do they have sales? Are you checking? Okay. So a telescoping series, you can extend it, and when you're done, you can kind of put it back together, and then you can pull it back out, put it back together. All right? So we call this the telescoping series. And here's why. Here it is in expanded form, but it also collapses back down into a condensed form. Here's why. If you get rid of the parentheses for the grouping symbols, what do you notice about some of the terms? They cancel. Negative 1/2 and positive 1/2 cancel. Negative a third and positive third cancel. Negative fourth and the next term would have a positive one. All of these terms cancel all the way down to infinity, all the way down the line. And they leave just what behind in their wake? In this case, a 1. So this is an infinite series, but you can actually find its sum. Okay? So this would be the second series for which we can actually find sums. Geometric series being the first, telescopic series being the second. Okay? So example 10. Determine whether the following series converge or diverge. If they converge, find their sum. All right, now, just like with integrals, if you have the sum of two terms, you can find the sum of each one separately. So let's do the nth term test on each term. 1 over 2n plus 1, as n goes to infinity, goes to 0, and the second term also goes to 0. So by the nth term test, these things might converge. Are they geometric? Do they look exponential? No, they look more polynomial-ish, right, which would be rational functions. So these are going to end up being maybe closer to P series. But anyway, we don't know if it converges or diverges or not. Okay. Now notice they're both growing kind of similar to like 1 over n, right? And we already know that 1 over n, the harmonic series, doesn't go to 0 fast enough. But we're subtracting some things out. So when in doubt for something like this, whenever you see a minus sign, just go ahead and start expanding some of the terms. Okay. So let's do that. When you plug in a 1, you get 1 over what? 3 minus 1 over 5. There's the first term. That's when n equals 1. Plus, when n equals 2, we get 1 over 5 minus 1 over 7 plus, now let's do n equals 3. You get 1 over 7 minus 1 over 9 plus ... Is this a telescopic series? Well, yeah, it would appear that some of these terms, if I drop the parentheses, would cancel out. The negative 1/5 cancels out with that. The negative 1/7 cancels out with that. Will the negative 1/9 cancel out with the next term? Yeah, it appears the pattern is that the second term in one set is the first term in the next set. So yeah, these should cancel out again all the way down the line. And in this case, we're just left with the first term again. So this series actually converges, and it converges to a third. It's a telescopic series. Okay? Pretty neat. Now, don't be lulled into thinking that all telescopic series cancel out this way, leaving you only the first term as residual. Sometimes there are other terms that are left. Okay, so let's try the next one. The integral not the integral, I keep saying integral, old habits. The sum from 1 to infinity of 1 over n times n plus 1. Now, if you were to distribute the n, this would look kind of like a 1 over n squared with some help, which you would guess would be what? Convergent or divergent? If it grows kind of like 1 over n squared as a single term, you would think convergent, right? The nth term test is inconclusive. The terms go to 0. But your intuition should tell you that this one what? Converges. And it does, okay? It does. Can we find the actual sum? Well, is it geometric? No. Is it telescopic? Man, it doesn't look telescopic. Telescopic has this very distinctive look. It's something minus something, so that when I expand it out, can I write this in that form? Can I decompose this into partial fractions? Yep, I can. So just like when we integrate using the partial fraction decomposition by the Oliver Heaviside cover-up method, which y'all learned when I was in the hospital from that nerd on the video, we can do it here as well, all right? So we split it up, and now we come back up here to the factored version, and we say, okay, n, when you plug in a 0, makes it 0, cover it up, plug a 0 into what's left at, and you get 1 over 1, which is now the new coefficient of what we covered up. The next one, negative 1 makes that a 0. Cover up that. You plug in a negative 1 for what's left, and you get 1 over negative 1, which is negative 1. So there you go. It's equivalent. Now it looks kind of telescopic. So now you can actually start expanding it. So you get 1 over 1 minus 1 over 2. Plus, plug in a 2, and you get 1/2 minus 1/3. Plus, plug in a 3, and you get a third minus 1/4. Plus, yada, yada, yada. Let's see, the 1/2s cancel, the 1/3s cancel, the 1/4s cancel. We're left with what? 1. Wow, so that thing does converge to 1. Pretty neat. So we can't always do that. Yeah, Tyler? Until you know for sure that everything cancels, okay? Until you know for sure. So here's the pattern I noticed. Again, in the previous term, the second term is the first term in the next sequence, okay? Again, the second term is the first term in the next, and if that continues, then you know it's going to divide out or cancel out, and you're left with just that 1 again. So until you're confident, I would say go on for more terms. If you're not confident, you'll see the pattern. Now you're not going to be asked to find the actual sum of this type on the BC exam because telescopic series is not part of the curriculum, but you will have to know that it converges. And you can tell that this one converges by intuition, or later on we'll do something called the direct comparison and the limit comparison, which will give it conclusively, okay? But in this case, I'm just telling you that there are some clever ways to find sums of things that are not geometric series. And here's one of them. All right, the next one. It's an infinite series. What does your intuition tell you? It's kind of growing like a 1 over n squared with some help. So your intuition tells you this one what? Converges, okay? Now, it's not a geometric series, so you're not going to be asked to find the sum, but can we find the sum? Maybe, right? Maybe. If I can factor the denominator as a product of 2 linear non-repeating factors, then I can decompose it into 2 partial fractions, which may, if they're opposite signs on the terms, it may be telescopic. Not everything that decomposes is telescopic, okay? Just like not every glass is a telescope. All right, so let's see if this factors first of all. So we get n plus 1, n plus 3. That's the first step. The next step is to get it set up with your denominators. And now we'll do the cover-up method to get our numerator. So if I cover up an n plus 1 and plug in a negative 1, I get 3 minus 1 is 2. I get a half. And if I cover up the n plus 3 and plug in a negative 3, I get a negative a half. And now I will simplify this since they're both the same. I'm going to factor the 1/2 out in front of the entire summation, the entire sigma, which is legal. Okay, the same algebra of integrals works here. And now because the signs of those two terms in the decomposition are opposite signs, this thing might be telescopic. Okay, so let's go ahead and start expanding it. The 1/2 now with the beefy bracket. Plug in a 1 and you get 1/2 minus 1/4. Plus, plug in a 2 and you get a 1/3 minus a 1/5. Plus, plug in a 3 and you get a 1/4 minus a 1/6. I'll go one more. Plug in a 4 and you get a 1/5 minus a 1/7. And then plus dot dot dot, close beefy bracket. All right, let's see if this one does telescope or collapse down. Notice this one's now a little bit different. The negative 1/4 does not cancel with this 1/3. Does the 1/3 even cancel, or does the 1/4 cancel? It does, but notice it doesn't cancel until over here. All right. Does the 1/2 ever cancel? No. Does the 1/3 ever cancel? No, it doesn't look like the 1/3 cancels. Does the 1/5 cancel? Yes. Does the 1/6 cancel? Well, let's see. What would the next term be? This was n equals 1, 2, 3, 4. The next one would be, if I plugged in a 5, it'd be 1 over 5 plus, be 1 over 6 minus 1 over 7. So yes, the negative 1/6 would cancel. Would the 1/7 cancel? Yes. So Tyler, here's where, if you're not sure, we're going back and we're just adding. Oh, that wouldn't be 6 and 7, would it? When it's a 5, it'd be an 8. It'd be an 8. But the 1/7 would cancel with the next one, okay? So you actually add more terms if you're not sure. And now I think I've got the pattern going. I've established enough so that everything, because notice the difference here of n plus 1 and n plus 3, the difference in the denominator is 2 instead of 1. And so now I think everything is going to cancel except what I didn't cancel. And now we have some residual other than a single term. So don't just expect it to be the first term. So this ends up being a 1/2 plus a 1/3. What is a 1/2 plus a 1/3? 5/6, right? And then 1/2 of 5/6 is 5/12. So kind of nifty. This one actually does converge, and that's really all you're going to be expected to know. But because it decomposes into a telescopic series, you can actually find its sum, which is 5/12. It's kind of nifty. Just to be able to know it converges is really, really cool. To be able to then say you have its sum, that's a whole nother level of awesomeness, okay? And now you can find it. All right, any comments or questions about telescopic series? Are they on the BC exam? No. Will you see series like these on the BC exam? Possibly, but then you're only going to be asked if they converge or diverge. Okay, did we find anything conclusive about Chipotle? Did it actually say in honor of Burrito Day we are charging full price? It actually said that. So it acknowledged that today was Burrito Day, but then said, "Phooey on you." Yeah, so, yeah, maybe Freebirds. Or Taco Bell, I don't know. Okay, the integral test and the P-series test. Two more tests. All right, the integral test. The integral test is the one that typically shows up on a free response, okay, if it's going to show up at all. So there are some qualifying things for the integral test. First of all, the function that you are finding the sum of, the rule of sequence, has to be decreasing. Now here's the thing. It doesn't have to be decreasing for all values of n. It just has to be decreasing forever and ever beyond a certain point. So you might have a series in the beginning that actually increases and then decreases and then increases a little bit, but then eventually after some point it does decrease forevermore after that. It has to be a continuous function. So it can't be like 1 over n, right? It has to be something that doesn't have gaps, jumps, holes, vertical asymptotes. And it has to be positive. Can't have negative values. Like we have seen, you can have negative values of r. So those are the three things that have to be there for the integral test. So to help you remember that, DCP, you can remember, if you ever incarcerate a canine, they don't like it, right? If you incarcerate a canine, they don't like it. Not unlike humans, right? But unlike humans, dogs will let you know. They'll start cussing, okay? So where do dogs cuss? They cuss in prison. Dogs cuss in prison. That helps you remember, right? Believe it or not, it does help you remember. Dogs cuss in prison. D for dogs, C for cuss, P for prison. Decreasing, continuous, positive, okay? Dogs cuss where? In the bathtub? No, that doesn't help you remember. Cats cuss in the bathtub. They don't like to get wet. Most dogs, my dogs at least, like getting bathed. Dogs cuss in prison, okay? For x is greater than or equal to 1 and a sub n equals fx, blah, blah, blah. Okay, so here's the integral test. Here's what it says. If you're trying to evaluate an infinite series and your rule of sequence is a sub n, if a sub n is decreasing, continuous, and positive, then if you integrate the exact same function a sub n from the same number to infinity, but now you do it as a function of x, then the integral and the sum are going to have the same behavior, okay? They're going to have the same behavior. They either both diverge or converge. And so because we have a way to evaluate an improper integral, that gives us then a way to determine the behavior of the series. So if the integral diverges, the series diverges. If the integral converges, the series converges as well, okay? But it has to be a dog cussing in prison. Got it? Is this a two-way test then? It should be a two-way test. We are going to be able to determine if it converges or diverges. So note that if they do both converge, it does not mean that the series converges to the same value as the integral. It doesn't mean they converge to the same value. And as I already mentioned, the function only needs to be decreasing beyond some point. Okay, so that's what that means, beyond some k for some k. Now there's another part here called the integral remainder, and I'll talk about that as well. It's not on the AP exam, but it will be on my exam. But we'll come back to that here in just a second. All right, let's first of all look at example 11. Determine whether the following series converge or diverge. If they converge, find an interval in which the sum resides using S sub 4. I don't know what that means yet, but we will figure that out. Okay, so here we go. We got the integral from 1 to infinity of n over n squared plus 1. Nth term test, never not first now. Nth term test. N over n squared plus 1 as n goes to infinity. Does it go to 0? Yes. Okay, so we know then that this series has a chance to converge. Okay, it still might not. What does your intuition tell you? What does your intuition tell you about this guy? Converge or diverge? Converge? Well, let's see. If you got rid of everything but the leading terms and simplified, n over n squared would simplify to 1 over n. And what do you know about 1 over n and his associates? They diverge. So your intuition should tell you that this one diverges. And you know what? It does. So if this were a multiple choice question, great. Now, to actually determine that, what's that? You winced or grimaced. Are you okay with why we said it diverged? 1 over n. You weren't here yesterday. Yeah, you need to watch the video if you haven't already. 1 over n, remember, like the integral from 1 to infinity of 1 over x, that dx, that was the gatekeeper for diverging. This is called your harmonic series. And it also diverges. If the power is greater than 1, as it turns out, we haven't talked about that explicitly, but we did look at 1 over n and 1 over n squared yesterday. So this is a harmonic series. So if it grows like a harmonic series, it's going to be divergent. Now let's prove it. If you have to actually prove it, you can't just say, my intuition leads me to this. Okay? You can either later on use a limit comparison test, or here's another way to do it. It's not a geometric series. If those n's were x's, would you be able to integrate this? That's the first thing you'd want to consider. Yeah, you would be able to integrate that. So now, is that dogs cussing in prison? Does this function decrease at some point? Yeah, as n goes to infinity, n squared plus 1 is bigger than n, so the terms are getting smaller. Is it a continuous function for all values of x greater or n greater than or equal to 1? Yeah, n squared plus 1 is never 0, okay? So that's good. Is it positive? Is it upbeat and optimistic? Yeah, it's also positive. There's no negative terms. So dogs cuss in prison, it applies. So now we'll go ahead and integrate from 1. If we started at 2 on the series, we would start integrating at 2. If we started at n equals 5, we would start integrating at 5. It starts at 1. So we're going to integrate from 1 to infinity now of x over x squared plus 1 dx. Okay? So an improper integral. And of course, if this shows up as a pre-response question, remember, the requirement is that this has to come from a limiting process. So let's remember that with notation. First of all, let's go ahead and get the integral. Your inside function is in the bottom to the first power. Its derivative is 2x. We're off by a 2, right? So we have a 1/2 correction. And now the x on the top gets packaged up, and it becomes the natural log of the absolute value of x squared plus 1. And we evaluate it from 1 to, remember it's a free response, b. Yeah, this would be the latest you can introduce the limit. You don't want to put infinity there. You got to put a b and then have the limit up front. Remember, if this is a multiple choice, you're already done. You know it diverges by intuition. All right, so let's prove it. I'll pull the 1/2 up front. We get the limit as b goes to infinity. b, if we bracket, we get the natural log of b squared plus 1. We don't need absolute values anymore because these are positive numbers, plus the natural log of 2. And now, what happens to b squared plus 1 as b goes to infinity? Goes to infinity. So what is the natural log of infinity? Or what is happening to the natural log as x goes to infinity? It approaches infinity. So that is infinity plus a finite number. Infinity plus a finite number is infinity. Half of infinity is still infinity. So we'll say here that this whole thing equals infinity. Okay? So the integral and the series do what? Diverge. Now you'd have to say this, since if you hadn't given the dogs cussing in prison yet, which I wouldn't even bother doing it until you know you can integrate it. Now you would say since n over n squared plus 1 is, and then just go dogs cuss in prison, is decreasing. Dogs cuss, continuous, and prison positive. Okay, so you can actually state that in the beginning. Your function, your a sub n function is decreasing, continuous, and positive, and then go ahead and integrate it, or you can wait till the end and throw it in your final answer, okay? So they have the same behavior. The integral diverged, therefore the series diverges because the series is decreasing, continuous, and positive. You don't even have to say by the integral test. You can say by the integral test, but you're actually doing the integral test, right? So you don't have to state the test you're doing. I mean, it's kind of nice, but you don't require it. Now, here's the cool part. With the integral test, you can't find the actual sum if there was a sum. But you can actually figure out an interval in which the sum actually lives, okay? And that's called the integral error. So remember, we can actually approximate the sum s, if we use s for the actual sum, with a partial sum, call it s sub n. The subscript means how many terms that we use, okay? So if you add up the first 4 terms to approximate the sum, that would be s sub 4. If you added up the first 10 terms to approximate the sum, that would be s sub 10. This is only for a convergence series, so not the one we just did. Now, of course, the more terms you add, the closer you're going to be to the actual sum. Would you agree? Yeah. But as soon as you quit adding more terms, you are not going to be the actual sum. But you are going to be able to figure out the maximum error. In other words, how far away you are from the actual sum. Not the actual amount of how far away you are, because then you know the actual sum. But you'll get an error bound, okay? So like if I add up the first 10 terms, I might be able to say, ooh, adding up the first 10 terms puts me within an eighth of a unit of the actual sum. So the actual sum could be like a whole eighth unit bigger or anything smaller than that, okay? That's called the error bound. And sometimes we call that the remainder. So R sub n is called the remainder which sometimes is called the error bound. It's an upper bound on the error, okay, using n terms. Okay, and it's the, well, actually, I'm sorry. I'm getting ahead of myself here. The remainder is the actual error. Sorry, it's the actual error. Okay, and how do we find actual error? It's the approximation subtracted from the actual, and then, of course, if we take the absolute value, we'll get it. We can't actually find the actual error, can we? If we could find the actual error, we would be able to find the actual sum. But we could say then that the error is bounded by the following, okay? The remainder, the actual error, which is the remainder, is going to be less than or equal to the integral from n to infinity, where n is the number of terms we use. So for instance, if we added up the first 4 terms for a convergent series, we could then say, I know that that sum is going to be within whatever the integral is from 4 to infinity of that function. Okay, it's not going to be exactly that amount, but that amount at the very most, or anything smaller than that. Okay, if I use the first 10 terms, then I know that my remainder is going to be within the integral from 10 to infinity of that sum. So let's try that out on part B, because this one's a convergent one. If you just did the nth term test for divergence, 1 over n squared plus 1, the terms go to 0. So the nth term test is inconclusive. But your intuition should tell you that because 1 over n squared is the rate at which this one grows, when you simplify, your intuition tells you that this one converges, because we saw that numerically up above earlier. It ends up being a p-series. So it does converge. Now let's prove it. If you had to prove it, again, you can't say intuition. So you have to use something else. So the first thing you want to do then is say, okay, is this geometric? No. It's not going to be telescopic, because it's n squared plus 1. That's not even on the exam. Can you integrate 1 over n squared plus 1 with respect to n? Yes. So here's what we're going to do. Let's check the dogs cussing in prison first, because if it's not dogs cussing in prison, actually, the integral test doesn't even work. 1 over n squared plus 1 is it decreasing? Yes, it's decreasing. Term by term, as you plug in larger values of n, the terms get smaller. Is it continuous? Yes, continuous. And is it positive? Yes, and positive. Good. So that's all you have to say. If you want to say so, the integral test applies, that's fine. So here's what we're going to do now. Now we're going to integrate from 1 to infinity of 1 over x squared plus 1 with respect to x. All right, what would be the antiderivative of 1 over x squared plus 1? Arctangent. So that's arctangent of x. Evaluated from what? 1 to what? B. Good. And now we'll put the limit as b goes to infinity up front. If this is a free response, this is what you'd have to do. Now, we'll evaluate it. The limit as b goes to infinity. That's going to be arctangent of b minus arctangent of 1. And, of course, now we can evaluate the limit. What is the limit as b goes to infinity of arctangent of b? Pi halves, right? It's the upper horizontal asymptote. That's pi halves minus, what's arctangent of 1? Pi fourths. Good. Now, you don't even have to simplify that, but it does come out to be pi fourths. This is finite. That's what's important. Now, what I said earlier is now, because the integral converges, so does the series. But the series does not converge to pi fourths. Okay? So now you could say, so the integral and the series both converge. Great. Now, we want to know what the sum is, but unfortunately it's not geometric, so we're not going to be able to find it. But we can get an approximation for the sum. So if you are asked to do this, and there is an error bound on the AP exam, but not the integral test, okay? the alternating series is, but it works the same way. You're going to be told how many terms to use. So in this it says, find an interval in which the actual sum can live using S sub 4. That means using the sum of the first 4 terms. Okay, so now that we know it converges, let's go ahead and figure out what S sub 4 is. Well, let's just go ahead and plug them in and add them up. When we plug in the 1, we get 1 plus 1, we get 1/2. Plus, when I plug in a 2, I get 2 squared, bless you, 2 squared is 4 plus 1 is 5. Plus, when I plug in a 3, I get a 10th. Plus, when I plug in a 4, I get 1/17. Now, these questions are typically calculator questions, unless they have you do like 2 terms, S sub 2. So let's go ahead and figure out what that is on a calculator. Since we've generated the terms already, you don't have to simplify that. On the calculator, you can either type that in, 1/2 plus a 5th plus a 10th plus a 17th, or we saw yesterday you could also do what? Do we have a sigma button on our calculator? Yeah. If my calculator would load, I'd show you. It is on alpha what? Alpha window? Yeah. I don't know why it's not showing up. Alpha window. So go ahead and do that. Maybe y'all can help me out here. I'm going to have to restart it. Alpha window, and then you go to number 2, I believe, right? So what is S sub 4? Oh, it's starting. Did anyone get it? 73rd, 85th? Okay, good. You do want to give it as an exact answer. So if it was an ugly decimal, you would want to store it. So let's say you had it as an ugly decimal, you would store it as A. All right, I can catch up with y'all now. So if you weren't here yesterday, alpha window, number 2 is your summation. And I'm in function mode, so I'll just leave it like that. So I'll use X starting at 1, and we went all the way up to 4. We added the first 4 terms. And it's, be careful if you don't use the horizontal division bar, 1 over x squared plus 1. Hit enter. All right, so yeah, it gave you a nice number. Okay, so there it is. And now, here we go. Let me go ahead and write it out. The remainder from using 4 terms as a sum is equal to S minus S sub 4, right? But we don't know what that is. So we do know an upper bound. That is going to be less than or equal to the integral now from 4 to infinity of 1 over x squared plus 1 dx. All right, so there it is. The remainder using 4 terms is equal to the actual minus the approximate, but we don't know what it is, so it's less than or equal to the integral from that same number 4 to infinity. So let's go ahead and evaluate this right here. We've already got the antiderivative, so it's the limit as b goes to infinity of arctangent of b, from 4 to infinity. 4 to b, Wait, did I do that right? That should be still x. My bad. Okay. Now if I plug it in, I get the limit as b goes to infinity of arctangent of b minus arctangent of 4. And of course, we've already talked about this. What is the limit as b goes to infinity? It's pi halves minus arctangent of 4. Is 4 a known unit circle ratio? I don't think so. So now if you wanted to get a decimal for that, you could. I'll go ahead and do that. Pi halves minus arctangent of 4. And we get 0.24497. I'm going to go ahead and store that as B. Okay? So what I would do on my paper is store that as B. So from the calculator, just hit stow alpha B. And the reason I want to store that as B is I do want to come back up here and store this one as A. Just because it's going to make it a little bit easier here. So if I stored it as A on my calculator, I would store it as, yeah, I would write it on the paper. Okay, so here's what we could do then. Now we could say the actual sum is going to live in, and because the terms are positive, I know that the sum is not going to be any smaller than 73/85. Would you agree? Because I keep adding positive terms to that, it's going to be slightly bigger than that. So I can use that as a lower bound. So I can say it's S sub 4 as a lower bound, comma, and then S sub 4 plus the integral from 4 to infinity of 1 over x squared plus 1 dx, which I just found, right? So let's go ahead and see what that's going to be. S sub 4, let me, what is that as a decimal? 73 divided by 85. So 0.8588. I'm going to put more than 3 decimals here. 88235.294. I'll write them all down. And then I could take that number plus, and I can add b to it, which is 1.103802193. 802.193. Okay, there you go. So even though we don't know what the sum is, we do know that the actual sum is somewhere in that interval. And it's kind of like a confidence interval in statistics if you've done that. I'm 100% confident, though, that the actual sum lives in that interval. What if I wanted to make the interval smaller? What could I do? Add more terms, right? If I just approximate it by doing S sub 5, now I get a number that's a little bit bigger and therefore a little bit closer, and then the integral is going to be a little bit smaller, okay? And so the more terms you add, you can make that window smaller and smaller. But there's a trade-off because, remember, doing this without a calculator is very, very, very tedious. Now, here's what we can actually do. We can kind of cheat, can't we? We're learning these methods that were really useful back in the day before computers. But now I can kind of cheat. I can actually take this summation process and very, very quickly go ahead and take it to, I'll just kind of keep in the spirit of what we did yesterday. If I take it to 2,000, let's see how long that'll take. That number should be between 1.076. Is that in our interval? All right, let's take a stand. Please remain standing for the moment of silence. Will do. The computer's working while we're moment of silencing. .076. We are pretty confident then to at least the third decimal place that the sum is 1.076. And notice 1.076 happens to live in our interval. So short of getting an actual sum, finding an interval in which it lives is pretty good. All right, we'll stop there and pick up tomorrow with example 12.